the gravity of something that we can't see must be holding those stars in their orbits, and that's evidence for dark matter. And in fact, galaxies are mostly dark matter. The stars that we see in these galaxies are like, again, sprinkles on this much larger mass of dark matter ice core. And again, we know it's there because of its gravitational effects. Again, skipping forward, just as we confirmed that fact in clusters of galaxies using gravitational lensing, we've also now confirmed the existence of dark matter in individual galaxies using the same gravitational lensing effects. So what you're seeing here are images of different galaxies, again from the Hubble Space Telescope. The yellowish blobs in the center is a foreground galaxy, and those bluish rings are actually the highly distorted images of another galaxy behind that foreground galaxy. And it's been distorted because the light from that distant galaxy was bent around by the mass of the foreground galaxy. And that very high lensing is again telling us about how much mass there is within the foreground galaxies. It's much more than the mass contained in the stars. Here's another example of this. This is actually a system we found with the Sloan Digital Sky Survey and then followed up using the Hubble Space Telescope. So again, the yellowish blob in the center is a foreground galaxy. The blue ring around it is the highly distorted image of another galaxy that's behind it. Okay, and finally we now do this on a kind of industrial scale where we can apply that same technique of lensing to study the shapes of galaxies behind thousands of foreground galaxies and do this in a kind of average statistical sense. This is called galaxy-galaxy lensing. And instead of probing the masses of individual galaxies, this lets us probe the sort of typical mass of average galaxies. And so we started using this technique back in the 1990s. And what we found, again, was that on average, luminous galaxies are embedded in these extended, what we call halos of dark matter. And so this was written up in the New York Times in late 1999. And apparently we were very surprised by this finding because that, to make it interesting for there has to be some element of drama. I was actually much more interested in the article on prehistoric fashion. That was the other article in the newspaper that day. Okay, so we've now established that dark matter exists. It's the dominant form of mass in galaxies and in clusters of galaxies. So the natural question is, what is dark matter made of? Is it made, so what could it be made of? Well, there's the stuff we know about in the universe. It's atoms, which is made of electrons orbiting around a nucleus. The nucleus, more fundamentally, is made of protons and neutrons. The protons and neutrons, more fundamentally, are made of quarks. And so you might think, okay, maybe dark matter is made of some kind of atom that just, for whatever reason, is not shining light or emitting or interacting with light in some way. So could dark matter be made of atoms, something that's very dark? And so in early times, people thought, okay, maybe there could be very faint stars that we just too faint to see, maybe planets that aren't illuminated by a nearby star, maybe some kind of dirty rocks. And so astronomers searched for these, but we gradually concluded that there simply aren't enough atoms in the universe to account for all of the dark matter that we infer in galaxies and clusters of galaxies. There's too much dark matter out there compared to the amount of atoms that we have added up in the universe that we've now measured very precisely. So dark matter must be made of something other than atoms, or more fundamentally quarks, the things we study here at Fermi. And perhaps it's made of some new kind of elementary particle that we've never seen before, that isn't, the atoms aren't composed of. And so our name for this is a weakly interacting massive particle, or WIMP. And so a WIMP is basically some new kind of elementary particle. It might be, say, 10 to 100 times the mass of a proton, which is so weakly interacting that we don't see it. It doesn't shine. It doesn't interact with light. But it could interact via the weak interaction with ordinary kinds of ordinary atoms. And so there are experiments around the world, sited deep underground, filled with atoms, as you've seen here. And they're looking for these WIMP particles coming from the dark halo of our galaxy. And the notion is that occasionally one of these WIMPs would come in, knock into the nucleus in an atom in this detector, and impart some energy into that nucleus, a very tiny amount. But if you have a sensitive enough detector, you can detect that energy that's deposited. And so there are a number of experiments now going around the world. Fermilab has an active program in searching for these dark matter, these WIMPs, using these techniques. There are a variety of different techniques. They all involve people wearing funny hats. This is an interesting field. There have been some of these experiments have claimed to have seen dark matter particles. Others that we think are more sensitive have not yet seen them. So it's an interesting time, and these experiments are getting more and more sensitive. And there's a hope that in the next decade, perhaps, we may actually detect in a verifiable way these dark matter particles. Another possibility is that we may actually produce these dark matter particles. You've all heard of the Large Hadron Collider at CERN, our sister laboratory in Switzerland, where the Higgs boson was discovered in 2012. They're bashing protons together at very unprecedentedly high energies. And the hope is that perhaps in one of these collisions of protons, they may produce dark matter particles, WIMPs, that we could infer through their signatures in these colliders. A third possibility for detecting dark matter is that we may see WIMPs annihilating with each other. So our current theory suggests that if there are dark matter WIMPs, particles, there would also be antiparticles floating around in the halo of our galaxy. And whenever a WIMP particle and antiparticle come close together and collide, they would annihilate, giving off a burst of energy, which would lead to radiation, high energy radiation, say gamma rays, that we could see if we have a gamma ray observatory. So NASA has such a gamma ray observatory orbiting the Earth, the Fermi Gamma Ray Satellite. And Fermi has been looking for signs of these anti-WIMP annihilations, looking both at the center of our Milky Way galaxy, which is very dense, so there may be a lot of dark matter there, and also looking at some of these other dwarf neighboring galaxies to the Milky Way, which are also very dense and would be places to look for this kind of annihilation signal. So Fermi is in the process of looking for gamma rays coming from WIMP annihilation. Okay, continuing on with the context, setting the basic facts of our universe. The fourth fact is that the universe is expanding. And this is traced to the work of Edwin Hubble. Hubble was an astronomer in the first half of the last century. And we have to talk about him because he was a graduate of the University of Chicago. Both his undergraduate and graduate degrees were there. He also studied law. He was a boxer. He did track and field. He played basketball in his spare time. He did astronomy. And Hubble did some really amazing feats in observational astronomy in the first part of the 20th century. He's the one who really proved that spiral nebulae, these wispy things, which we now call galaxies, he's the one who proved that they are actually galaxies outside of our own Milky Way. Before then, there had been great uncertainty whether these nebulae were actually clouds of stars within our own galaxy. And he discovered the expanding universe in the late 1920s and went on to make important catalogs of galaxies and sky surveys. So here's a picture of Hubble using the Palomar 48-inch telescope. So does anybody notice anything odd about this photograph of Hubble using the telescope? Well, he's not looking through the telescope, he's looking through the viewfinder, but yes, exactly, the lights are on. So to do astronomy, the lights have to be off. It has to be dark. So, I sort of have my doubts about, how authentic all this stuff really is because, you should have known to turn the lights on. Anyway, before that, Hubble had a quite stellar athletic career. So here's Hubble with the 1909 National Championship, before the NCAA, I think. National Championship basketball team, 1909. And here is actually Hubble's basketball, championship basketball, on the space shuttle with the Hubble Space Telescope in the background. The final score of that championship game was University of Chicago 18, Indiana 12. I think it took them a while before Steph Curry hadn't been invented yet. They didn't have three-pointers back then, so nevertheless, Hubble really went on to a brilliant career in astronomy, and to celebrate his career, astronomer John Grunsfeld, also a Chicago graduate, brought his basketball up to on one of the missions where they refurbished the Hubble Space Telescope. Okay, so here's the expanding universe. As time goes on, everything in the universe is moving away from everything else. If you were to run this movie backward in time, eventually everything would be on top of everything else. 13.8 billion years ago, that's what we call the Big Bang. And I wanted to stress a few key points about the expanding universe. One is we're really talking about the distance between galaxies increasing. We don't think our galaxy is expanding. We don't think this room is expanding. I'm expanding, but that's because I eat too much. Generally, within our galaxy, gravity is keeping things sort of stable. So it's really the distance between galaxies which is increasing with time. And again, to give you a sense of scale, a galaxy 100 million light years away is moving away from us at 2,000 miles per second. So the universe is kind of humming along. Again, this was really established by Hubble in the late 1920s. Now, there are a lot of misconceptions about the expanding universe, and often many of these misconceptions are traced to the fact that this picture, while useful, we have to be cautious in interpreting it, because we're looking at a lower dimensional universe from our three-dimensional perspective. So we don't think the universe has a center or an edge, at least not that we can see. It looks the same everywhere. It's homogeneous and isotropic. And the expansion is happening everywhere. It's not exploding into empty space. And so really that picture of an expanding balloon is somewhat misleading. It's probably better to think of, say, an infinite raisin bread. Think of the raisins as galaxies. You put enough yeast into it and put it into the oven, and it will start to expand. Each raisin will move away from all of the other raisins. That's probably a better analogy for the expanding universe. Another point to make is that as the universe expands, like any gas, it gets less dense and it cools off. Therefore, if we run the movie backward in time toward the Big Bang, it becomes hotter and denser. So today the universe is very cold. It's only 3 degrees above absolute zero and very diffuse. The density of the universe is very low. But in the early universe, it was much hotter and much denser. And so this is now our best picture of the early universe, cosmic microwave background radiation. This is as seen from the Planck satellite. So this is an all-sky image of the temperature of the universe as it appears today, 3 degrees above absolute zero. So the red and blue splotches are regions where the temperature is slightly hotter and slightly colder than the average. And that slight is only 1 part in 100,000. So the universe, to first approximation, has the same temperature everywhere, but it has these slight differences in temperature from one place to the other. Now this is really giving us a snapshot of what the universe looked like when it was only 380,000 years old. It's now 13.8 billion. So this is really a picture of the adolescent universe. And at that time, it had a temperature of a few thousand degrees. But since then, with the expansion of the universe, it has cooled to a temperature just below 3 degrees above zero. So this is a picture of what the universe looks like today. This is a map of galaxies from an infrared survey done a number of years ago. Each of the little white squares there is the location of a galaxy. There's a few million galaxies in this picture. The blue is just, this is in funny coordinates, so the blue is actually infrared emission from our own galaxy. And again, what you see here is that the universe today is actually quite lumpy. It's not obvious what the contrast is here, but the lumpiness of the universe today is orders of magnitude larger than it was 380,000 years after the Big Bang. And so our picture is that as the universe has evolved, it started from nearly homogeneous conditions. The density of the universe was almost the same everywhere in space. Whoops. But then, over time, gravity acted on slight differences in the density between different locations in space. Regions that were denser than average accrued matter onto them. Regions that were less dense than average became more and more vacuous. And eventually, large-scale structures formed. This kind of web, this thing we call the cosmic web. So this is a computer simulation of the evolution of structure from nearly homogeneous initial conditions to a very inhomogeneous universe that we see today. And in this simulation, the only ingredients are gravity acting on particles and dark matter particles, for example, WIMPs. They didn't even bother to put in atoms in this simulation because they're a small minority compared to the dark matter. And this simulated universe looks remarkably like that lumpy universe of galaxies that we actually see today. So our picture of the history of the universe is that it started in a Big Bang 13.8 billion years ago, started expanding very rapidly. That's a period we call cosmic inflation. Once it had reached about 380,000 years after the Big Bang, that's when the photons, the radiation in the microwave background started streaming away from the atoms, and that gives us this picture of the microwave background that we saw from Planck. And then over the succeeding billions of years, those small fluctuations in the temperature and density of the universe evolved via gravity into the large-scale structures we see today: galaxies, stars, planets, and larger-scale structures. So that's the picture we have now of how the universe has evolved. So we know the universe is expanding, and it's natural to ask, is the expansion changing over time? So what do we expect? Well, again, gravity is the dominant force on large scales. And so we can do a simple thought experiment. We're sitting here on the Milky Way. We look at all these other galaxies, these billions of galaxies. They're all receding away from us due to the expansion of the universe. But our galaxy is tugging on each of those galaxies because of gravity. We're exerting a gravitational force on all those billions of galaxies moving away from us. And therefore, we would expect that if we observed any one of those galaxies next year, 10 years from now, 100 years from now, the speed with which it's moving away from us should reduce over time. It should be slowing down because we're pulling on that galaxy. And so that was the expectation through much of the 20th century, was that the expansion should be gradually slowing down over time. And Hubble and many of the people he taught and worked with and who followed him tried to measure that slowing down of the cosmic expansion and never could do it because it was the measurements are very challenging to make. And then in the late 1990s, two teams of astronomers studying distant supernovae in fact found that the expansion was not slowing down. They both found evidence that it was in fact speeding up over time. And this was led to the Nobel Prize in Physics in 2011 for the leaders of those two teams. So I want to talk a little bit about this discovery and some of its implications. So this is a supernova. This is the kind of event those astronomers were looking at. So this is a nearby galaxy. In the lower left, you see what looks like a bright star. That's in fact a star in that galaxy which exploded, and about 3 weeks after it exploded, it became nearly as bright as all the other billions of stars in that galaxy. So supernovae are remarkable events. They go from being fainter than the sun to being brighter than a billion suns over the course of just a few weeks, and then they fade over the course of a few months. And this is a gallery of about 500 supernovae that we discovered in the mid-2000s using the Sloan Digital Sky Survey. And again, what you do is you look at, you make a big survey of the sky, you come back sometime later, you look at the same patches of the sky, and you see if there's anything new there. And each of these blue splotches is a new star. It's a supernova that wasn't there when we took the images of those galaxies a few weeks before these. We think, so these supernovae that we're looking at are a particular kind of supernova called the Type 1a supernovae. And we have good evidence that Type 1a supernovae are explosions of what we call white dwarf stars. These are very compact stars. Our sun will eventually, we think, become a white dwarf star once it's finished burning all of its nuclear fuel, and it will become very compact and dense. And if you have a white dwarf star near another star, and either accreting material from it because of gravity, or else orbiting another white dwarf star and eventually colliding with it, in both of those cases, the mass of the white dwarf will increase until it reaches the maximum mass, called the Chandrasekhar mass, about 1.4 times the mass of a sun, and then it will explode. It will undergo a thermonuclear explosion, and it's those explosions and the radiation from those explosions that lead to these supernovae events that we see. And so these two teams of astronomers in the late 1990s, what they could do, what they realized was that these supernovae, these Type 1a supernova explosions, all had about the same brightness. When they, about 3 weeks after they exploded, they reached their peak brightness and then faded. And they had determined that all of these supernovae had the same intrinsic luminosity. So they were all like 100-watt light bulbs, obviously much brighter, but all 100 watts, not 80 or 120. And so this means that these particular kinds of supernovae are what we call standard candles. And if you know how bright something is, then you can determine how far away it is relative to other supernovae. And so what they were able to plot was essentially, we could tell how big the universe was when they were exploded. That's the redshift. We can tell that from the spectrum of light. And then they used the brightness of these supernovae to essentially tell how far away they were, or alternatively, how far in the past they had exploded. And what we had expected was something like this black line, that a supernova that went off when the universe was 2/3 its present size would have a particular brightness. But the points there are showing you that instead, a supernova that went off when the universe had a certain fraction of its current size was actually about 25% fainter than we expected. And that was the indication that the expansion of the universe is not slowing down due to gravity, but is in fact speeding up. And that's what led to the Nobel Prize discovery. So why is this a strange phenomenon? Why is this a mystery? Well, you know, whenever you have any kind of object, every time you've taken any object and you've thrown it up and dropped it, whenever you throw up a ball, as soon as it leaves your hand, it's moving upward, but what's happening? It's slowing down due to gravity. It's attracted to the center of the Earth. As soon as it leaves my hand, it starts to slow down, and because I can't throw very hard, eventually it reaches some maximum height and then falls back down to Earth. And every time you've thrown a ball up, that's what's happened. And that's because gravity is attractive. But what the universe is doing is sort of like, imagine I throw this ball up, and initially it starts slowing down due to gravity, but then at some point, instead of continuing to slow down and eventually hitting a maximum point and falling back to Earth, instead it starts to speed up and rockets out of the atmosphere of the Earth into outer space. That's what the universe is doing. Safe to say we've never seen that in our everyday experience. But that's why the acceleration of the expansion, the speed up of cosmic expansion, is a mystery. It's because it confounds our understanding of gravity. So what could be causing this speed up of the expansion of the universe? And we basically think there are two possibilities. The first possibility is that the universe is filled with some kind of stuff that gives rise to a kind of repulsive gravity. Gravity is usually attractive in our everyday experience, in the solar system, in our galaxy. But perhaps when we're talking about things on cosmic scales, there is some additional stuff in the universe. It's not dark matter, it's not atoms, it must be something else, which has the property that it makes things repel from each other and therefore speed away from each other. We now call this dark energy. And we think that the universe is 70% dark energy. That's one possibility. The other is that maybe something strange is going on with gravity when we get to cosmic scales. Again, in the Earth, the solar system, our galaxy, gravity obeys Einstein's theory of general relativity. It's attractive force. But again, perhaps when we get to very large scales, gravity behaves in a different way, in such a way that things can accelerate away from each other. So that's the second logical possibility, is that there's something going wrong with our understanding of gravity. So we now have this picture that's been put together just over the last 10, 15 years, that 95% of the universe is dark, doesn't emit with a light or interact with light. So the stuff we see in our everyday world, stuff made of atoms or more fundamentally quarks, that's only 5% of the universe. So the stuff we're trying to figure out the nature of, primarily here at Fermilab and elsewhere, that's only 5% of the universe. The stuff that we know about, the laws of physics that we know of. We think 25% is this dark matter. It's not made of atoms. It's made perhaps of some new elementary particle. And that's the stuff that's holding galaxies and clusters of galaxies together, and is the engine by which galaxies, with gravity, by which structure forms in the universe. And then we think the dominant component of the universe, 70%, is this dark energy, this gravitationally repulsive stuff that's actually speeding up the expansion of the universe. Dark energy is not something we observe in our everyday life. It has no tangible effects, again, on terrestrial scales. It's much too dilute, too weak a force. So it would only come into play on cosmic scales. Let's skip over that. So one interesting thing is, I said that the universe today we think is about 70% dark energy. That's if you look on the right-hand column, about 20% dark matter, about 4 or 5% atomic ordinary matter. But if we go back in time, then those relative amounts of those different components will change. We think that as the universe expands, dark matter becomes more dilute, ordinary matter becomes more dilute, because as things get, as the distance between them gets bigger, the density, the mass per unit volume goes down. But that doesn't happen with dark energy. So since dark energy is dominating today, as the universe, we think that the density of dark energy hasn't changed very much from today to earlier times. And that means if I go back in time when the universe was denser, higher density of dark matter and ordinary matter, that means dark energy was relatively less important. So if I go back to a time 9.5 billion years after the Big Bang, the middle column there, then we think the universe was about 50% dark energy, 43% or so dark matter, 7% ordinary matter. And if I go even further back in time, to just 1 billion years after the Big Bang, then we think dark energy was only 1%, dark matter was the dominant component, 84%, ordinary matter about 15%. And this is important because remember I showed you that movie of structure forming by gravity. That only works in a universe where the bulk of the stuff is dark matter. Once dark energy takes over, becomes more dominant than dark matter, structure can no longer form because dark energy is this repulsive force pushing things away from each other, where gravity was the thing pulling them together. So we think that before a few billion years, the universe actually was slowing down due to the gravity of dark matter. And then maybe 7, 8, 9 billion years after the Big Bang, dark matter became sufficiently dilute that dark energy took over and caused the universe to speed up. So what is dark energy? Well, we don't know. We think it's a component with negative pressure, and that's what we need in general relativity to make something which will be gravitationally repulsive. But we really don't have a good fundamental understanding of what dark energy is. Our most conservative hypothesis is that it's the energy of empty space itself, the vacuum. So if I took this bottle of water, poured all the water out of it, put a vacuum hose on it, evacuated all the air from it, shielded it from cosmic rays, there would be no particles left in it, no ordinary matter. I could shield it from dark matter, and it would be empty space. In classical physics, empty space would have no energy. But in quantum physics, empty space has energy due to Heisenberg's uncertainty principle. And it turns out that in quantum mechanics, the energy of the vacuum would have the right properties to be dark energy. It would have this gravitationally repulsive effect. So that's the most conservative hypothesis. Now, the only slight problem with that hypothesis is that if I calculate how much energy there is in the vacuum in this little bottle of water, it's infinity. And I'm pretty sure there's not an infinite amount of energy inside this bottle. So that means that our calculations are wrong. And this has, in fact, been a major embarrassment for theoretical physics for the last century. We just don't have an understanding of why the vacuum, the energy of empty space, is not infinity or much larger than we observe it to be. So it's still a fundamental mystery. There are other suggestions for what the dark energy could be. One popular idea is that perhaps the energy of the dark energy is associated with a much, much lighter cousin of the Higgs boson, a different kind of field permeating the universe. But those ideas are even much more speculative. And so I thought what I would do would be, when you don't have the answer to something, you ask Siri. So Siri, what do you think the nature of dark energy is?
I'm sorry. I'm afraid I can't answer that.
Yeah. Okay. Well, it was worth a shot. Okay. I think Apple should be working on this better. But okay. All right. So we don't know what dark energy is. Siri doesn't even know what dark energy is. Nevertheless, dark energy is important. Why is it important? Well, the nature of dark energy is going to determine the future evolution of the universe. It's already 70% of the universe. I said it was a smaller fraction in the past. That means in the future, dark energy is going to be an increasing fraction of the universe. So it's dominating now. It's going to dominate, we think, into the future. And so we need to understand its properties if we were to have